today. And again, fellas, today is going to be airflow and duct design. It'll be part 2 of our 2-part series that we're doing with you today. Okay, so everyone, Tony, I'll let you kind of be the scribe a little bit like you do oftentimes. Can you see the screen okay? All right, so someone go ahead and...
Yes.
Okay, so you can see the screen. Okay. All right. Well, good morning again. One more time. We're going to be getting into our second part of our 2-part series of our airflow and duct design. And so at this time, we're going to go ahead and practice some duct design based on velocity recommendations as a main consideration. Now, I know oftentimes we're taught in trade schools, and perhaps some, we've learned from a previous family member or whatnot. And some engineers, excuse me, and some engineers, they certainly prefer what we call the static loss method or the friction loss method, which is fine because according to Manual D, and this is a quote right out of Manual D, there are 2 sizes associated with every duct section: the size that satisfies the airflow requirement and the size that satisfies the velocity limit. Now, the final design is always based on the larger of these 2 sizes. Now, just as a little bit of a history lesson, if you will, oftentimes we learn in trade schools and we learn, in textbooks and so on to utilize what we call the friction loss method or the static method, the static loss method, which is going to satisfy the airflow requirement and allow us or guide us to build a duct system with the smallest duct that we can get away with and still satisfy the airflow requirement. However, Manual D clearly states in Chapter 3 that there's 2 sizes associated with every duct section: the size that satisfies the airflow requirement, in other words, the friction loss method, and the size that satisfies the velocity limit, which is also called the velocity limit method or the velocity method of designing duct systems. The final design is always based on the larger of these 2 sizes. Now, just as a point of reference, guys, put this in your back pocket, write it down, make a note of it. The velocity method will always give you a slightly larger duct system. And so what we're going to be doing today, we're going to be focusing in and studying the velocity method of duct design. Now, maybe you haven't used this method before. It's very, very simple. Basically, we're going to take our duct calculator. We're going to design around a target velocity. We'll then plug in the CFM off our duct calculator. And then at that point, we'll be able to see what size duct we need. Now, from a practical boot on the road, so to speak, standpoint, from a practical field standpoint, what this means is most of the time, especially on short runs, your duct size is going to be about what you've been using all along. However, if you have a longer run, or if you've got a spot like, for instance, on a takeoff where you'd normally use like a 6-inch duct, we may find that we're using a 7-inch duct now to satisfy the velocity limit. As far as the main trunk size, when you're doing the velocity method, you're going to notice that you're going to be upsizing your main trunk a little bit too. Now, the result of all this is going to be a quieter system, a more efficient system, and overall, yes, you'll have a little bit more material, or you'll have a little bit larger duct size, but when you think about the actual true cost of installing a little bit larger duct system, it's not going to be significant because your labor is fixed and all that already anyway. So we're going to be utilizing the velocity method because the final design, again, quoting from Manual D, the final design is always based on the larger of these 2 sizes, and that's going to be the velocity method. Now, we're going to also ask that you please note that all duct runs, takeoffs in other words, should be equipped with a manual damper for final airflow balance. And so unless you've got a duct system that is absolutely perfectly designed as far as the length of the duct and stuff like that, we find that in most applications that a method of balancing that airflow into each space, into each conditioned space, is going to be very, very important. So we recommend that during installation, go ahead and plan on a damper on each takeoff so that you can do final airflow balance when you're done. And as you saw yesterday, we have methodology of actually knowing how much CFM is moving through a duct system, either with a rotating vane tool that we talked about or a hot wire anemometer as we start commissioning our duct systems for proper airflow. Any questions or comments so far before we continue?
No.
Pretty good? Okay. Well, let me move my chair just for a second here. I've got behind me in my office an actual duct calculator like what we've been using. So I'm going to do these same examples with you. Here off screen, I'll be using the same ductulator that we have on the PowerPoint. And so we'll be working together today as we start looking at building a duct system based on the velocity method. So let's just do a typical supply system on a 3-ton unit. We know down in Florida quite often you're going to have a central return. So we'll just presume we're going to have a central return. That's pretty common down there in Florida, so we'll just do that. But let's talk about building that supply trunk based on a 3-ton unit. Now remember, team, we talked yesterday about 400 CFM per ton. 400 CFM per ton is going to be our nominal airflow for our, when we're sizing our duct system. So we want to make sure that we kind of remember to do that. And I'm working on my screen now, real quick, just as a quick little reminder for me. Can everybody see the screen okay? Or do you have any like blacked out spots or anything like that? Because sometimes on my PowerPoint on my screen, the little block where I have people's pictures in the lower right-hand corner sometimes puts a little black spot on the screen. So does everybody see the PowerPoint screen okay?
Perfect.
Okay, all right, so it must just be my display then. Okay, so guys, what we're going to be doing, we're going to be building a 3-ton unit, a trunk. We're going to be building a duct system for a typical 3-ton unit, and we're going to size all of our main trunk components. All of our main trunk components, we're going to be utilizing a velocity method of 700 feet a minute. So basically, when we go in and we start sizing our duct system for our main trunk, we're going to be considering the main trunk velocity as per Manual D yesterday when we looked at our velocities, recommended velocities for a main trunk. We're going to size those at 700 feet a minute. So we need 1,200 CFM on a 3-ton unit. So at 400 CFM per ton, we need to start out with a trunk off the air handler that's going to be able to carry 1,200 CFM at 700 feet a minute velocity. All right, so with that in mind, so what I'm going to do is I'm going to give you one side. I'm going to give you one side of the duct, and I want you to find the other. So take your calculator right now and go to 700 feet a minute velocity and twist and turn your duct calculator until you've got 700 feet a minute velocity at 1,200 CFM. So we want 700 feet a minute velocity at 1,200 CFM. Now, once you get that, hold your duct calculator steady. And we want I'm going to give you one side of the main trunk dimension. You tell me what the other one is. So at 700 feet a minute velocity, 1,200 CFM, we're going to have a 14 by what size duct to provide that? A 14 by all right, so
26.
Okay, so a 14 by I had a 14 by 19. So make sure that on your duct calculator, I'm going to tell you what I'm going to do real quick. So does everybody have their round duct calculator like we talked about yesterday when we went through some of those exercises?
We have a self-work version.
So is everybody good on that? So take the velocity of 700 and line it up with 1200 CFM. Then come down below a 14 by 18, 14 by 19 is what I've got on my duct calculators. Does everybody have the same number?
Yes. Yes.
Okay. All right, good. So this first section of trunk, before we do any takeoffs, that first section of main trunk, fellas, is going to be a 14 by 19 if you manufacture it. Now, someone said, well, gee, Joel, we buy all of our ductwork prefab, and nobody makes a 14 by 19, but we can either go a 14 by 20 maybe, or a 14 by 18. My recommendation would be to go ahead and go up to the next size of 14 by 20. If you could get a 14 by 20, go ahead, do it, or 14 by 18. I'd probably go with the 14 by 20 just so it'd be a little bit quieter. And even though the duct velocity would be like maybe a 680 or 670, I'd rather have it a little bit quieter unit. But you guys can make that decision. If all you had available to you was a 14 by 18, that would be okay too. It's just that it would jump the velocity up to maybe 725 or 750, which would still be within range. So you could get by with a 14 by 18 as well if you're buying pre-manufactured duct. But if you make your own duct, a 14 by 19 would nail it just perfectly on a 700 feet a minute velocity on the main trunk. So that first section of duct that we've got on our main trunk in this example is going to be a 14 by 19. That's before we do any takeoffs. Now, on the takeoffs themselves, all of our branch runs, let's go ahead, according to Manual D velocity table that we looked at yesterday, the recommended velocity for branch runs or for takeoffs is 600 feet a minute velocity. So as we take a look at our takeoffs, when we start doing takeoffs, let's just remember we're going to size our branch runs, our takeoffs, at 600 feet a minute velocity as per Manual D recommendations. And so this is a real easy way to design a duct system. I've done this for over 20 years, probably 25 years, and it works very, very well, gives you a nice quiet system and so on. The only downside, if you will, of this method is the fact that your ductwork is going to be a little larger, and so there may be a little cost difference between what you may normally have been doing and a little larger duct system. So, but it's well worth the money. It's well worth the installation difference because, frankly, it'll give you a really good duct system. It's going to be quiet and efficient, and that's the main thing. So as we start doing our branch takeoffs, a couple of things we're going to presume. Fellas, now there's different ways to determine how much CFM you need in each space. But the best way to do it is to do a Manual J heat load calculation on the house or on the structure before you build a duct system. And so you do your Manual J heat load calculation, and part of that heat load calculation will tell you how much CFM into each space. So whatever method you're using to determine CFM into each conditioned space, bedrooms and bathrooms and living room or whatever, that method is fine, whatever you're using to determine the amount of CFM. The point is we have to know the CFM in each space before we build a duct system to it, right? So we're going to presume right now that you know how much CFM you want in each space. And we're going to also presume that I know how much CFM on the PowerPoint I want in each space. But just keep that in mind. Before you build a duct system, be sure you know how much CFM you want in each room or in each space. So with all that said, our first takeoff here is going to be 135 CFM into that conditioned space. I've already determined that by whatever method I use. My favorite method is Manual J, room by room heat load calculation. That's what I do. That's what I use. Like I said, there are other methods to do it, And at the conclusion of our training today, if you'd like to discuss that as a side topic, we can certainly do that to determine how much CFM you have in each space. But for whatever reason or whatever method I've used, I know I need 135 CFM into this first space. So with that said, at 600 feet a minute velocity, take your duct calculator and find 600 feet a minute velocity and line that up with 135 CFM. And let's see how much we're going to need in there. So we've got
I apologize, Joe. Would you repeat the question?
Yeah, what size duct do we need for 135 CFM off this first takeoff? What size
6
duct?
or 7.
Okay, good, excellent. 7-inch, good. Give yourself a star. That is correct. So 7-inch duct is what I've got on my calculator as well, at 135 CFM. Our next run is 150 CFM at 600 feet a minute velocity. At 600 feet a minute velocity, so 700. 600 CFM at 150 CFM at 600 feet a minute velocity. What size duct do you need for that one? Still a 7-inch,
7.
right? There you go. Okay, so another 7-inch run. Now in the past, maybe you ran a 5 or 6-inch run, but we're seeing that with the velocity method, we upsize our duct a little bit. Typically, with the velocity method, gives you a quieter system. And remember, guys, we're going to recommend you put a damper on each takeoff anyway, so that you can do your final airflow balance into each space. And then our third run, there you go, is 145. That's right in between those two numbers. So again, a 7-inch run. Is that correct?
7.
All right, now, before we transition down, now, let's have a little talk about this. So Manual D recommends that before you have to transition down, to go ahead and that they allow, Manual D allows up to 40% of your air before you have to transition down in that duct section. However, we find that most contractors, after 2 or 3 runs, they'll go ahead and transition down. So let me open the floor up for just a minute or two. When do you guys normally transition on your main trunk to the next size down? How many takeoffs do you normally take off before you transition down on your main trunk?
Possibly 3.
Up to 3. Okay. And that's pretty common in the industry. Now, if you want to get technical, you can transition after 1 if you want to, but that's normally not practical to do that. So we find that most contractors will take 2 or 3 takeoffs on a trunk before they transition down, which is fine as long as you don't exceed 40% of the air in that particular section of main trunk.
Does that apply with the flex?
It's going to apply with anything, basically. So when you transition down, when you transition down, you want to make sure that you don't take any more than 40% of the air in that particular main trunk section. Don't take any more than 40% off. And like I said, typically we find that most contractors, it ends up being about 2. Normally after about 2 takeoffs, or maybe 3 smaller ones or medium-sized ones, they'll go ahead and transition down, which normally works just fine. So good questions. All right, so now what we're going to do, because we've taken some air off this first section of main trunk, it's going to be time for a transition. And so we're going to transition down. We're going from a 14 by 19. And let's just keep that 14 dimension and go down to a 14 by something. But let's figure out how much air we have left over. So take your calculator, and we started out with 1200 CFM. And if you subtract 135, 150, and 145 from 1200, you should end up with 770 CFM left over. Go ahead and do that for me on your calculator to make sure that my math is good on our PowerPoint. So we started out with 1200 CFM, and we've taken off 3 runs. 135 CFM, 150, and 145 CFM. So we add those numbers together, subtract it from 1200, and we should end up with 770 CFM left over. Is that a good number?
Yes, 1410.
Okay, so you're ahead of me there. I had a 14 by 13, but let's double check that. So at 770 CFMs left over. Now remember, we're going to be going up to 700 feet a minute velocity on our main trunk. So the main trunk velocity target is 700. The branch run is 600. So take your duct calculator and take 770 CFM. That's what we have left over, and line that up with 700 feet a minute velocity. And we should have about a 14 by 13 is what I had.
Yes, the same.
Is that a good number?
Ours has it slightly off.
So 770 and 700 feet a minute velocity. I've got like a 14 by, it's right in between 14 and 12. So I've got like a 14 by 13 for 770 CFM on that main trunk. Is you guys getting that okay on your duct calculator?
Yes.
Okay, good. So our next section of trunk fellows will be a 14 by 13. And we're moving, so what we're doing, we're taking that 770 CFM that's left over, and we're squeezing it down, and we're moving it through a transition, and we're speeding that air back up. Now, this is important. We want to keep the velocity in the main trunk at the proper velocity, moving that air down that main trunk. That's why we have transitions. The reason we have a transition is because we want to increase the speed of that air back up to its target 700 feet per minute. So what the air we have left over, in this case 770 CFM, we want to make sure that it continues to move down the duct at the proper velocity, so that we have good throw out the registers on our branch runs. So that's the big deal. We want to make sure and transition when we need to, and keep that velocity moving down that main trunk. So the next takeoffs we're going to do, we have 90. We've got a pretty small space, so we have 90 CFM at 600 feet a minute velocity. So take your velocity and go down to 90 CFM at 600 feet a minute velocity. And what size duct do we need to make that happen?
6.
So I like your answer. It actually came up about 5.5. Well, nobody makes a 5.5 inch duct, a round takeoff or whatever. And if you're using flex, 6 inch which should be going to you go to 6 inch on that one with a damper, so you can do final air balance, because you only need if you take a look at your duct calculator, 5.25 inch duct to provide 90 CFM at that velocity. However, nobody makes that size duct, so you go to a 6 inch duct, and you'd put a damper on there so that you can do final air balance. And then we have another run at 125 and another run at 125. So at 600 feet a minute velocity, let's zip up to 125. And what's our duct size?
6, 7.
Okay, because it's it's about 6.5 inch on a round duct. I'd probably jump up to 7 as well, because I'm going to put a damper on there. I'm going to put a damper on each takeoff, and so if that takeoff's a little bit oversized, I can still control the amount of air coming out of it with a damper. So having a damper on your takeoff, on each takeoff, really gives you the flexibility to really dial that airflow in on each duct, and more specifically into each space. And so once you've got all that dialed in, you'll be able to take your rotating vane tool or your hot wire anemometer, and you'll be able to dial in the exact airflow into each space like you've designed it. So now with all that said, so we've got 90 CFM, 125 and 125. So let's add those numbers up, 125 plus 125 plus 90. And then whatever that number is, subtract it from 770 to see how much air we have left to move down the rest of the trunk. So take 90 on your calculator plus 125 plus 125, and whatever that number is.
330.
Okay, so 430. That sounds about right. Excellent. All right, so let's go ahead and we're now you'll notice on my PowerPoint there's no way on the PowerPoint to build a transition that you just move like one side, and you'll notice that there are actually four-way transitions on the PowerPoint. But from a practical field standpoint, most of the time what's going to happen, sheet metal shops, they'll build a transition. They'll take just one side and they'll fold it in. As you guys know, you've seen transitions out there. They'll just kind of fold it in. So don't really look at the PowerPoint. Just know it's a transition, and the fact that I couldn't draw in the PowerPoint, or I couldn't pull in the PowerPoint anything other than like something that looked like a four-way transition. But we know that it's going to probably be a two-way transition, or where they just folded the side in. But with all that said, at 430 CFM, that's what we have left over. Now remember, we've got to go back to 700 feet a minute velocity on the main trunk. So at 700 feet a minute velocity, we've got 430 CFM left over. 430 CFM left over. And so what size trunk are we going to have for that last little bit of air? A 13 by
8, 9.
That sounds about right. I've got a 13 by 8 as well on my calculator. So this last section of trunk, to handle that 430 CFM, we're going to speed that air back up to 700 feet a minute velocity. And we're going to put that last section of trunk out there. Now, guys, you're going to notice that I've capped off the main trunk, and I've done my takeoffs. And this really isn't to scale. That last takeoff is like about 2 feet. Is going to be like about 2 to 3 feet from the end cap. Now, let me ask you cats a question. Why would I stretch out that piece of main trunk as long as I've got room to do it, cap it off, and then have my last takeoff, a couple feet from the end there? Why would I do that?
Maintain pressure, velocity.
Oh, I love that answer. Give yourself a star. That is correct. It maintains pressure in the duct system, because if I was to take that last takeoff and just kind of take it off the very, very end, it would actually depressurize the whole system. And so that's very, very good duct practice, is as long as you've got room to do it, stretch that main trunk out, that last main trunk component out, cap it, and then back off a couple of feet on that last takeoff. Now remember, team, you're going to have dampers on each takeoff, and so you'll be able to balance the airflow very, very nicely. And so taking a look at those last 3 takeoffs, what size duct would I need on those last 3 takeoffs for 145, 145, and 140? What size duct would I need with a damper?
8.
Okay, good, excellent. So so as we build our duct systems out, we want to be very, very aware that if we design our duct systems with with velocity in mind as our main criteria, we'll always have a nice quiet system. It'll perform properly, and if we put dampers on each takeoff, we'll be able to balance that airflow perfectly. And fellas, right now, this duct system that we've just built together, if you built a duct system similar to this in design, I promise you that system would allow you to properly charge your unit, and it would also give you a wonderful humidity control and quiet operation. As a matter of fact, you would be able to deliver, as long as it was sealed up nice and well insulated, the ductwork was well insulated, you'd be able to deliver 95% capacity of that system's capacity into the space where it belongs. And by the way, one of the main reasons that systems do not perform properly, the number one reason systems do not perform properly is airflow. And so airflow is the most important thing that you can do on an install. And then right behind that is keeping your refrigeration system clean. You know, use nitrogen when you raise your lines up and all that stuff. Keep your refrigeration system really clean and dry. Get a good double evacuation. But if you'll do those two things, keep your refrigeration system clean and dry when you put your unit together, and give it the proper airflow at the proper velocity. Those are the two top things that you can do to make a reliable, comfortable, quiet system. Everything else is secondary. You know, you could, you know, if your line set was a little bit long, you know, you can work around that, you know, if you know, and so on and so on. But if you get the airflow right and you keep the system clean and dry, those are the two top things that you're going to have to build in reliability and comfort for your homeowner. Any questions or comments on this duct size exercise that we just performed? Any questions or comments?
No, sir.
Okay, good. All right. Well, let's talk a little bit about measuring airflow now. So once we build a duct system, we're going to have some method of commissioning that duct system. And so we're going to teach you two different methods now. Actually, it'll be a third method because we learned earlier yesterday that we could use a rotating vane anemometer, the little whizzy wheel guy, or a hot wire anemometer, and we can actually put it into the ductwork, or, you know, take the register off or what have you, and we could determine airflow by looking at the duct size and, you know, measuring the duct size and measuring the velocity of the air. And we went through all that yesterday, and that's a good way to do that. But I'm going to teach you two more ways this morning on how to measure airflow, because once you design a duct system and you're balancing the ductwork and all that, once you design a duct system, we have to be able to commission it and to make sure that we're getting the proper airflow through the unit. So the first method we're going to talk about this morning is what we call the external static pressure method. The external static pressure method is a method where we're going to measure the total static pressure in inches of water column on the supply and the return duct system. Now, guys, remember the fan's designed to move air through the duct system by providing a positive air pressure on the supply side and a negative air pressure on the return. To find external static pressure, we got to do the following steps. Number one, we're going to measure the supply side air pressure with a magnehelic gauge or a digital manometer, and that's going to be a positive pressure. We then are going to measure the return side air pressure, which is a negative pressure because the fan is sucking, right? So we're going to measure that pressure, and then we're going to add those values together. Now, this is important. You're going to notice that on your magnehelic gauge or your digital manometer, it'll have a positive pressure on the supply, and there will be a little negative sign on the return side because it's a negative pressure. Now, fellas, you don't have to do algebra. You don't have to take, let's see, a positive pressure and a negative pressure, and, you know, you don't have to do that. You just add the numbers up. You don't have to worry about positive and negative. You just add the numbers up. To give an example, let's say I've got a 0.3 inches of water column on my supply and a 0.15 negative on my return. Well, I add those together for a total of 4.5 static pressure. And so I just wanted to stress that we don't have to, we know it's a negative pressure on the return side, but we're just going to take the number. We're not going to worry about the negative sign. We're just going to take the number and we're going to add them together to give us total external static pressure, ESP. And then we're going to go to our factory airflow charts, and we're going to look at the airflow charts to determine how much airflow is moving through that system from the factory airflow chart. So all of our factory airflow charts, guys, are going to be based on this external static pressure. So when you take a look at any of my air handlers or any of my furnaces or even my commercial stuff, you're going to be looking at external static pressure as part of the measurement to determine what is the airflow moving through that system. Now, this is important. You've got to have the proper tools, right? So if you don't have good tools, you're wasting your time. And so that's about all I got to say about that. So make sure you've got the proper tools to do this. And so we're going to show you that proper tool right now. So this happens to be one in my own tool bag. I've got it just happens to be a field piece, but UEI makes them, Fluke makes them. I happen to have a field piece, dual port manometer and pressure switch tester. And there's a picture of it right there. That's right out of my own tool bag. And so the way to use this, you're going to select which port you're going to use, P1 or P2. You can select it right there, and that's going to be the ports on top. And then you're going to zero the meter. You want to make sure you zero the meter. And the reason you want that is because, you know, sometimes just because of temperature or what have you, you know, the meter may not be zero. So always zero your meter. And then you're going to attach a hose to the selected port. And then the other end of that hose is going to go to a static pressure probe. Now there's a special probe for doing static pressure. It's called a static pressure probe. And so one side is going to be attached to the meter. You're going to select what port you want. I happen to be on P1 or port 1 in the photo right here. And then I'm going to take the other end of that hose and I'm going to go over and I'm going to attach it to the static pressure probe. Now the static pressure probe is used to provide that static pressure to the manometer. You'll notice that static pressure probe has got some little holes in it. It's got a pointy end, and you always want to remember that pointy end of that static pressure probe goes into the airflow stream. It doesn't matter if it's supply or return. So you're going to have to position it so that the pointy end always goes into the direction of airflow. You're going to attach the hose from your manometer to that other side on that static pressure probe. So if you guys take a look at this, these are the proper tools you have to have. Again, one more time, you're going to have a digital manometer. You're going to select the port you're going to use, and then you're going to hook that hose to this static pressure probe. Now, as you do that on your unit, there's an example of how you'd hook that up. So on the supply side, you're going to poke a hole in the ductwork, and you're going to make sure that the pointy end is going into the airstream. And on the return side, because the air is coming the other way, you're going to poke a hole in your return duct, and you're going to make sure that the air is blowing in or going across the pointy end of that probe. Any questions or comments so far on how I would apply these tools, and then we'll start taking some static pressure examples here. Any questions or comments?
No, thank you.
Everybody good? Okay, now it should be noted, I know you guys probably don't have much of a furnace market down here, down there in Florida, but if you do have a furnace, you have to put the static pressure probe on the supply side underneath the coil, because the coil is not included on the static pressure charts for a furnace. On that rare occasion, you might have a furnace down there. However, on an air handler, this is important, make a note of this. On an air handler, when you take a look at the static pressure charts, the airflow charts from the factory on an air handler, the coil's already included. Now take a look at my cursor real quick. Watch my cursor. You see my cursor on my screen? All right, so if I have a filter right here, let's say I've got a filter where my cursor is, what I'm going to want to do, I'm going to want to take my static pressure right here where I've got it on the return, but I'm also going to want to take a static pressure reading after the filter. I like to take them both because what that does, that gives me an idea how much pressure drop I have across the filter. And so I recommend 2 return statics, either that or take the filter out, and then that'll give you your true static pressure that the fan is actually seeing. And then if you want to put the filter back in and take another one just to see how much pressure drop you have across the filter, that's not bad practice. That's actually pretty good practice. But just remember right now, if your filter happens to be between where I'm taking my static pressure reading right now on the return, if that filter's like right here where my cursor is, then make sure that you understand you're going to need to take it on the other side of the filter as well. That's just good practice. If you don't have a filter right here, but you do have a filter, say up here someplace, you know, in maybe a main filter grill in a hallway, then go ahead and take it right here where we have it on the return static, and that will automatically, the filter will be automatically part of that airflow measurements. So just be aware of those things, that filters will have some pressure drop across them. So just consider those things. So step number one, we're going to measure the supply side pressure and we're going to mark it down or make note of it or remember it. Step number two, we're going to measure the return side static pressure and make note of it, mark it down, remember it. However, we're then going to add those values together to get external static pressure and then refer to our factory airflow charts to see how much air is moving through this system. So let's go ahead and do that. Let's do some practice. So everyone should have some JHET air handler charts as part of the class. And so go ahead and we're going to refer to those, but let's talk about how this chart works. And by the way, if you can use this chart, you can use any of our charts. They all are set up the same way. The information may be a little bit different. The model may be a little bit different, but it's all essentially the same method. So number one, you're going to determine the model number. If it's a furnace chart, you determine the model number. If it's an air handler, you determine the model number. You cats get the idea. So you determine the model number of the product that you're looking at. And then so once you determine, and you find the proper column, determine the model number, you're then going to determine what speed tap that motor is on. So you're going to have to take the service panel off and you're going to have to look at and see what speed tap the motor's running on when you're making your airflow measurement. So naturally, if it's a cooling call, you want to make sure that whatever cooling speed that you have selected on your air handler, that's the speed that it's on for your static pressure measurement. So again, determine the model number, determine what speed tap you're on, measure your external static pressure. Now, please make a note of this. When you measure your external static pressure, make sure you've got all the panels back on. So you know what model number it is, you've looked at the speed tap, you put your service panel back on, and then you take your static pressure reading. And so in this example, we have a 0.4 inches of static, 0.4 inches of static, that's total. And on medium speed tap on that B24C air handler, as our example, we're actually moving 625 CFM through our system. And so remember, team, now this is how much air that's actually moving through that cabinet, that's moving through the system. So if you've got a good tight duct system, and it's sealed up nice, you can presume that that's what's moving through your ductwork. Now, if you have a sloppy duct system and there's holes in it and it's, you got cracks in it and whatever, this isn't necessarily the air that's moving through the ductwork unless it's a good, tight, well-designed duct system, right? So we're actually measuring the airflow at the unit, at the cabinet. So in this example, at 0.4 inches of static, we're moving 625 CFM through the air handler. Any questions or comments on how to utilize this chart before we do some examples of actually measuring some airflow? Any questions or comments?
No, sir.
Everybody good? All right, let me ask everybody, we're up to about an hour right now. Does anybody need to take a break? We're about 20 minutes from the end of the course, but does anybody need a break, or do you guys just want to push on to the end?
One moment, I do have a question coming.
Okay.
One more second, I apologize. The higher the static, the lesser the movement.
Okay, we had a question. Go ahead.
If it shows higher static pressure, is there less air moving? Like, would it be a restriction in the line or a blown out line?
That's an excellent question. Yes. So if the static pressure is too high, the two most common causes of static pressure being too high is maybe you have a piece of duct board that broke loose on the inside, or a piece of insulation that broke loose, or it's undersized duct. So if the static pressure is too high, you're not going to move the proper amount of air through the duct system. And the two most common causes of that is you have something broke loose in the ductwork, or the ductwork is too small. Good question. That's an excellent question. Okay. So let's go ahead and do some examples together. So as you can see, I've got my magnehelic gauge hooked up in my graphics here. And so my first reading, and so take a look at your JHET airflow chart. And we have a B36D, so that's the model number, of B36D, and we're on medium high speed tap, So referring to the chart, B36D model number, medium high speed, and my first reading, my supply static pressure is a 0.32 inches of water column. So 0.32. So write that down or remember it. My return static pressure is a 0.18, And so let's add those numbers together. A 0.32 plus a 0.18. We take a look at that together. 0.32 plus 0.18 equals a 0.5. So taking a look at your chart, a B36D air handler on medium high speed tap with a 0.5 inches of static pressure, what's the CFM?
1225.
And give yourselves a star. It's no more complicated than that, team. It's that simple. So you find the model number, you find the speed tap, you measure your static pressure, and you go to the chart. And in this example, this is a 3-ton air handler, so it's probably hooked up to a 3-ton unit, and a 0.5 inches of static pressure total. We're running right at 1225 CFM, which is just about perfect for a 3-ton unit. Any questions or comments on that? Okay, good. Let's do another one. So in this second example, we've got a 0.61 on the supply, and it's a B30D air handler, and it's on high-speed tap. And so go ahead and find that model number. You're on high-speed tap, so the technician has put it on the highest speed he can put it on to get his airflow. 0.61 on the supply, which is pretty high, but write that down or remember it. And then on the return, it's a 0.18, about like the other one had, which is a pretty good number. By the way, you want to have most of your energy. We talked about this yesterday. You want to have most of your energy on the supply side, which this one definitely does. And a 0.18 on return. And so if we add those together, a 0.61 plus a 0.18 is a 0.79 inches of static pressure total. So a B30D air handler on high speed tap, 0.79 inches of water column total. What's the CFM?
925.
Okay, 925. Now, guys, I want you to think about something as you take a look at this. So, and this is the main reason I like taking my static pressure separately. Now, some technicians, they'll have a dual port manometer and they'll take both static readings at the same time. I don't do that. I like to use one port and take them individually and then add them up. And the reason is sometimes you can get erratic readings if you're taking both of them at the same time. Especially on the old magnehelic gauge, it'll sit here and bounce around. So the number one reason for taking these readings individually is so I just have an isolated pressure that I can look at on each side, and then I just add them up. So that's my preferred method. The other reason I do that is that it will help me look at where I have a problem on a duct system. Now, this is a 2.5 ton air handler. And so if it's hooked, it's already on high speed tap. It's blowing as hard as it can, and I'm still about 70 to 100 CFM shy on a 2.5 ton unit. If I had this on a 2.5 ton unit, I need about 1,000 CFM at 400 CFM per ton. But this thing is blowing as hard as it can, and it's still not making full CFM. Now it's close. Would it still work? Probably. But I'm telling you right now, this system's probably going to be pretty noisy. It's going to have, you're moving close to the proper CFM, but this thing's on high speed tap. It's blowing as hard as it can, and it's still not making the full CFM that it should. And so as I take a look at it, the second reason I like taking static pressure readings on, supply and return individually, it helps me troubleshoot where the problem is. So on this duct system, I've got a 0.18 on return, which is pretty low. I mean, that, if you have like about a 0.2 or 0.25, that's normally acceptable. So that's pretty nice duct system on the return side. But look at that supply side duct pressure, 0.61. So if I was going to start remediating or looking for problems on this unit, I'd start looking where? On the supply or return side for my static pressure, for my restrictions. Where would I start looking? Anybody?
Supply.
There you go, supply. So that's the second reason I like taking those pressures individually, because it helps me figure out which side of the duct system I'm having issues on. And so in this example here, we've got high static. We've got unusually high static on the supply side. So I'm going to get up there and I'm going to take a look at that duct work. I'm going to see what size it is. I'm going to see if there's some kinks in it. I want to see if the TV man was up there a couple weeks ago and maybe he stepped all over my duct work and smashed it down or whatever. You get the idea. So I recommend take your pressures individually. That way you can start utilizing your magnehelic gauge and your static pressure as a troubleshooting tool as well. And in this example here, we are light on airflow. There's something going on the supply side. So that's where I'd start looking. Any questions or comments on utilizing static pressure and the factory airflow charts to find airflow? Any questions or comments?
Yes, 1 second. How would a dirty coil restrict the airflow in that study?
That's a really good question. So basically what you'd find is that if you had a dirty coil, what's going to happen is the fan's going to be trying to blow against that coil. But now remember, because the coil is included on an air handler, and we're taking static pressure on the supply side, downstream of the coil, we would actually see as the coil got dirtier, the static pressure on the supply side would actually start coming down. It'd actually start coming down. So let's say, for instance, on a brand new unit, we commission the unit and we find that we've got, we'll just use this example. Let's say we know we got a brand new unit, or maybe it's we just got done cleaning the coils and stuff like that. It's a 0.61. And the next time I come out next year, it's a 0.58 or it's a 0.57. Well, something's changed. And what that is, it could be a dirty coil. It could be a dirty air filter. Because if you think about it, the fan can only blow what it sucks, right? And so anything that's going to affect that fan ability to move air through that duct system will be reflected in that static pressure. Now, a little side note. On an air handler, as I said, the coil's included on that chart. However, on a furnace, the coil's not included. So you got to sneak under the coil and put your static pressure underneath the coil on a furnace. Well, on a furnace, if the coil was restricted on top and I take the pressure underneath that coil, guess what? We would find that it was a higher static pressure trying to build up and push through that dirty coil. However, downstream on an air handler, on a coil downstream, if the coil's dirty, the fan can't push it or pull it through that coil like it should, and so we'd actually see a decrease in that typically. So that's a good question. Now on a variable speed air handler, on an ECM air handler, the other thing you'd also notice is the fan is really ramped up and really, especially on variable speed, is just really trying to move that air. So I guess the moral of that good question is, the moral of the story on that good question is, make sure before you do any static pressure readings, make sure you got a clean coil, make sure you got as much air moving through the system as you can, and make absolutely certain that you've got a clean filter for these tests. So good. That was a good segue into make sure your coils are clean before you do all this stuff. Good question. Any other good questions or comments on static pressure and how we can use the factory airflow charts to determine airflow on our air handlers? Everybody good?
Could we please have a 5-minute bathroom break?
Absolutely. Let's go ahead and take a 5-minute break, and let's see what time it is. I've got about 7:50, so let's pick it back up at 7:55 or 8:55 your time. How does that sound?
Thank you.
You bet.
Hey, Joel, are you there?
I am. You guys ready to kick it back off?
I have a quick question about this reading. If it's a free draw, how would you register the return in that instance?
That's a good question. What you're going to do is actually go into the cabinet, just poke a hole in the cabinet. If it's just free draw, you know, like let's say for instance you had an air handler in a shop or something where it's just sucking through the back. Go ahead and just poke a hole in the cabinet and make sure the static pressure probe is you know, still pointing in the direction of the airflow. So instead of like going in the ductwork, you'd actually poke a hole in the cabinet just on the return side of the fan, so you could see what the fan was sucking. That'd be the way to do that.
Thank you.
Yep. Good question. All right, team. Well, I'll tell you what. With that good question, let's go ahead and kick it back off. Was there any other good questions about external static pressure other than on the free draw question we just had? Any other good questions or comments?
No, sir.
Everybody good? Okay. All right then. Well, let's go ahead and kick this back off then. Fellas, another method of measuring airflow, which has been around a long, long time. And all it requires is a temperature probe and an amp probe and a voltmeter. So you can, you know, these are normal tools you'll find on any service truck is an amp probe and a voltmeter and just a temperature probe. And this is what we call the temperature rise method, So the temperature rise method says this is the mathematical formula for it. It says this: CFM is equal to the output of the device in BTUs divided by 1.08 times delta T. Now that delta T portion of the formula is the difference in temperature between supply and return air temperature. So basically with a temperature probe, a voltmeter, and an amp probe, you can figure out what the output on an air handler is by looking at the heat strip and energizing the heat strip and making sure the compressor is not on during this operation. And by the way, the 1.08, that's a formula for sensible heat rise of standard air at sea level. So if you were up in Colorado, you'd have to shift that number a little bit, maybe to 1.06 or 1.05, because the air density is less as the higher you go in altitude. But for all practical purposes, this formula is going to work fine up to about 2,000 or 3,000 foot altitude. And I wouldn't think there in Florida that you'd have much chance of any of that being above a couple 3,000 feet. So this formula is going to work very, very good for you. So the temperature rise method. So CFM is equal to the output of the device in BTUs divided by 1.08 times the temperature difference of supply and return air. So let's plug in some numbers. So let's say, for instance, how do we do this? So what we're going to do, we're going to energize the heat strips and make sure that whatever speed tap we're testing, we're on the desired speed tap or we're on the desired airflow. We also want to make sure the compressor's off. So if we're testing speed tap number 4, we want to make sure we're on speed tap number 4. We energize the heat strips and make certain that that airflow call is coming on, and we want to make sure the compressor is off. So just throw the disconnect outside on the compressor, make sure the outer unit is off during this check. So we're going to energize the heat strips. Step number 2, we're going to take the voltage and the amperage with the unit running on the heat strips. So we're actually going to go to the disconnect on the indoor unit, and with the unit running, with the heat strips cooking and energized, we're going to measure the volts and the amps with the heat strip on and the motor running on the selected speed tap. Then we're going to multiply the volts times the amps times a mathematical constant of 3.414 to find the output portion of the formula for BTUs. So that's how you convert BTUs. Amps times volts times 3.414 equals the BTU output of that unit with the heat strips on. Step number 3, we're going to measure the supply and return air temperature within about 3 feet of the air handler. And the reason we want to do that is we don't want the heat strips actually cooking. We don't want the heat strips directly cooking, so to speak, on the temperature probe. So just go down about 3 feet down the plenum, and if you can't get it If you have a real short supply plenum, just go to the very, very first register, the very, very first outlet will get you close enough. So, but ideally it's about 3 feet from the air handler, and you're going to take your supply air temperature and your return air temperature, and you're going to find the difference of those. You're going to find the difference between those two temperatures and then multiply it by 1.08 to plug that formula in. Then what we're going to do, we're going to divide the output that we found, volts times amps times 3.414, divided by 1.08. And so basically the results of step number 3, and that'll give us that CFM. Now, fellas, it takes a lot longer to talk about it than it does to actually do it. It's a pretty simple process. So let's go ahead and plug some numbers in. Take your calculator as we find airflow on the next couple examples with the temperature rise method. So in our first one here, it's a 2-ton unit. So we want to find out if our 2-ton unit is moving 800 CFM, because remember, 400 CFM per ton. So we're shooting for 800 CFM on a 2-ton unit. So in our first example, we've got the heat strip cooking, we've got the indoor fan blowing on the desired speed tap that we're testing, and the outdoor unit is off. So with the indoor unit running and the heat strips cooking and all that stuff, we find that we've got 249 volts, and we have an amperage of 33.6. So we're going to take volts times amps times 3.414 to convert it to wattage, or output, I should say, to convert that to output. And so take volts times amps times 3.414, and somebody help me out. What's the output of that heat strip and all that with this cooking at 249 volts, 33.6 amps times 3.414? What is the output portion of this formula?
28,005.
Excellent. 28,563 is what I've got. And so write that down someplace or just make a note of it. 28,563 is what I have on my calculator. Next step we're going to do is so write that down. The next step we're going to do is we're going to measure the temperature between the supply and the return. My supply air temp is 105 degrees. My return air temperature is 72 degrees. So let's find the difference. The delta T is the difference between supply and return air temp. So if I take 105 and I minus 72, I've got 33 degrees. But hang on a second, we're not done yet. We've got to take that temperature difference and multiply it times 1.08. So take 105 minus 72, that's the temperature difference, times 1.08. And what's that number? So it'll be 33 times 1.08.
35.6.
Sounds about right. So that's that portion of the formula. So let's take that 28,000. Now let's go ahead and do the math. We take 28,563, that first number that we wrote down, and we divide it by, what do we say, 35.6, and that will give us the CFM that's moving through that air handler and across that heat strip. What's the CFM in this example? So 28,563 divided by 35.6 equals what?
802.3.
I had 802. Now, isn't that the coolest thing? So just by energizing your heat strip and selecting the speed tap you want and plugging in a little math, you can actually determine the airflow that's moving through that unit. And by the way, fellas, this is extremely accurate. I mean, it's going to get you within a couple percentage points of an airflow hood. I mean, this is very, very tight airflow. It's a lot tighter than you'd think it'd be in a field application, but it's all simple math, and it works very, very well. And I've used this method for years on air handlers, quick, easy, fast way to determine airflow moving through a unit. When I go out and commission or take a look at a job, if I have a problem job or something, it used to be when I was in the field, I use this a lot. Let's do one more just to make sure we've got this. So let's say it's a 4-ton unit. So we're looking for 1,600 CFM, 1,600 CFM on a 4-ton unit. So as we take a look at it, we energize the unit. We got the heat strip cooking, and we've got it on the selected speed tap we're testing. And we take the actual voltage at the disconnect of the indoor unit with it running on the heat strips at the desired speed tap, and we have 241 volts. And we take our amp probe and we measure 50.1. So take 241 on your calculator, 241 times 50.1 times, got to remember that 3.414 constant for finding BTUs. So volts times amps times 3.414. Tell me, technicians, what is the output portion of this formula?
41,220.
Excellent. That's good. I had 221, but that's close enough. So write that down, or make a note of it. Just remember it or write it down. So 41,221. I'm going to write it down myself right there. And now let's do the second portion of the formula where we take our temperature. So we take our temperature probe, take a good quality temperature probe, just stick it, make a little hole in the supply and return. I've got 92-degree supply, 72-degree return for a delta T portion of that formula of 20. So 92 minus 72 equals 20. But hang on, we're not done yet. We need to take that 20 degrees and multiply it times 1.08. So 20 times 1.08 equals what?
21.6.
21.6. Got it. Good, excellent. All right, now let's go ahead and plug that formula in. So we have 41,221 is the output under those points of measurement. So take 41,221 and divide it by 21.6, and that will give us the CFM in this example. Now we're looking for 1,600 CFM on a 4-ton unit, right? So what is the CFM? 41,221 divided by 21.6. And our formula, how much CFM? There you go. Well, hang on a second, though. 1908. So here's the complaint on the unit. It seems to be running fine and all that stuff, but my unit seems kind of noisy, and it's kind of sticky and humid in the house when the unit's running. Well, I'm pushing 1,900 CFM on a 4-ton unit, and I need 1,600 CFM. So if I'm moving too much airflow in the cooling mode of operation, is it going to take the humidity out like it's supposed to? And the answer is absolutely not. So in this example here, we're moving too much CFM. And yes, you can move too much CFM, especially in the cooling mode, because what's going to happen is you're going to lose your humidity control, right? You guys know all about that down in Florida. And so we're going to slow the fan down, aren't we? In this example, we're moving 1,900 CFM, and we want to move 1,600. So maybe we're on high-speed tap. So maybe we'll take it down to medium speed or medium high and measure it again. And the point I'm making with this temperature rise method, by the way, fellas, is you can use this any time of the year. You don't have to. It doesn't have to be in the wintertime. You can energize the heat strip in the summertime if you need to, for air, just quickly, for just a few minutes, to take an airflow measurement on whatever selected speed tap that you have. Just remember, you're going to have the outdoor unit off, and you're going to energize the heat strip, and then you're going to select whatever speed tap you're testing, and you're going to find the airflow. So this works in the wintertime. It works fine in the summertime. Just remember, if you're doing it in the summertime, you don't want to put too much heat into the house, obviously, but this is a quick, easy way to confirm airflow. And I've used this method for 40 years, over 40 years. as a technician, and and actually I've been in this industry almost 50 years now. Next spring will be 50 years I graduated technical school, and I learned this way back then. And so this is a very old method of airflow measurement, but it works very, very well, especially on air handlers with a heat strip. So with that, let's go ahead and open up the floor for any final questions or comments. Let me get the PowerPoint off, which is my habit. And let's go ahead and get everybody back. We'll get everybody back on camera and all that kind of stuff. And we'll open the floor up for any final questions or comments as we start heading towards the end of our training today. I hope everybody enjoyed it. But let's open that floor up for any final questions or comments on our airflow and duct design part 2.
1 second. I have someone asking a question from my iPad. 1 moment.
No problem. The team is
so if the system does not have heat strips, would a magnehelic be the end result to get a better reading?
I really like that question. That's a good question. So if you don't have heat strips, you wouldn't be able to use the temperature rise method, would you? That's a good point. And so if you don't have a heat strip, go ahead and use the static pressure method, or with your magnehelic gauge or your digital manometer and the factory airflow charts. And so, really in our training the last couple of days, we've learned how to measure airflow 3 different ways, haven't we? 3 different ways: with a rotating vane anemometer, the little whizzy guy, or the hot wire anemometer. We've learned how to use the static pressure charts, the factory airflow charts. And then we learned a third method, the temperature rise method. To your point, if you've got an air strip, or not an air strip, but if you have like a heat strip in your air handler. Now, this is important. If you call our factory support line, if you call our dedicated wind supply factory support line for our champion product down at the factory, our guys are going to ask you what your airflow is on a unit when you call down there and talk to our factory support folks. Now, they're presuming, kind of to fill out this answering question, they're presuming that you're utilizing the factory airflow chart. So from a factory standpoint, we really want you to use that static pressure chart as your first line of defense, so to speak. But we also know from our training today, we have a couple other methods that we can utilize as well. But the preferred method for the factory folks is going to be the factory airflow charts. Good question. Any other good questions or comments?
No, sir, that's it.
Well, I'll tell you what, then I want to thank everybody, for training with us today. I'm going to go ahead and stop the recording. The recording will be out on the YouTube training channel a little bit later on today. It'll be Airflow and Duct Design Part 2 for Mighty Air, and today's date, 11/29/2023. So I'm going to go ahead and stop the recording. And while I do that, thank you and have a good day with that.
Thank you again, both of you. Thank you.
Yeah, thank you guys. We sure appreciate you and appreciate the opportunity to train with you today, and we'll look forward to talking again sometime soon.